My screen is visible, right? The PowerPoint presentation slide.
Yes.
Can anyone? Yes, okay, right. We can start right now. Welcome to the fifth session of problem solving of NPTEL course, IC engines and gas turbines. So, my name is Ananthakrishnan. I'm a PhD candidate from IIT Delhi. I do this problem solving session as part of my PMRF TA duty. In this week, the main lectures focus on heat transfer and energy distribution in the cylinders and the IC engine cylinders, and they briefly told the cetane number and octane number systems, which we have seen in one of our previous problem solving sessions. We also have discussed a few problems regarding cetane number and octane number, and also cooling systems. And which all are the main cooling systems, air cooling as well as water cooling systems. And the last lecture of this week was on some problems on IC engines, where the professor had discussed a few of the basic problems. In this week, we will be briefly touching upon a few multiple choice questions on the heat transfer, heat transfer and energy balance between the cylinders, and also a few questions on the CT number and octane number, and we will solve a few numerical problems of IC engines. So general problems which will help you to deal with the quizzes and assignments better for NPTEL course. So let's move into the first question. Uh, is a question visible?
Yes, sir.
Okay. So can anyone of you give the answer for this question? So the question is regarding the energy balance within the cylinders. Uh, the heat given to the cooling medium in IC engines is about. So as we have seen in the previous lecture, the four main heat losses or the heat energy transfers which is occurring in IC engines will be mainly the first one will be uh, heat transfer uh, to cooling medium. There will be some exhaust losses. Third one, there will be some parasitic losses. And fourth one will be uh, the energy output, the power output.
It should be B, I guess, sir.
Yes, yes, right. So the answer will be the heat given to the cooling medium in IC engines is this one. So it will be the heat taken by the cooling water jacket or the lubricants means or lubricants. So that will be around 30 to 40 percentage. That and the heat transfer via exhaust will be the amount of enthalpy taken away by the exhaust gases, and the parasitic losses will be the amount of energy required to operate to compress the air. The energy which is being produced, the power which is being produced in uh, the power which is being produced in the power stroke, right? A part of that will be used to compress the air in the compression stroke. So that will also be an energy, and also the net power output, the break thermal efficiency, break thermal power. So that also will be a part of the total energy produced. So the total four will be combining together to give 100%, and out of that, the heat transfer to the cooling medium or water jacket will be comprising close to 30 to 40%. The second one is also regarding water cooling system. Mostly radiators are used in that kind of systems. So the question is regarding the function of radiator. The radiator is actually provided to cool the water jacket, pressurize the cooling water, provide additional water flow, or none of the above, which is the answer.
A, I guess, sir. A.
Right, right. So the radiator is actually in the case of air cooling system, we do not require any other external devices to cool air as continuous supply of air is available as the engine moves. But in the case of water cooled system, infinite amount of water is not available to cool the system, right? So we have to somehow ensure that the energy, the heat taken out by the heat absorbed by water should be released somehow. And that is being done by using this radiator setup where it acts by the principle of change in density. So hot water, which the water which absorbs energy from the engine cylinder gets heated up, and but the density of the water will be light, and that will be going upwards, while the cold water will be going downwards. Uh, after exchanging heat with the incoming air. So this is the process which is be used in most of the engine vehicles in the previous era, where the heat taken out by the water jacket will be released in the radiator to get a cooler water to complete the circulation around the cylinder. So the answer is the radiator is provided to cool the water from the water jacket. Okay. The third question is regarding the thermostat which are being used in the radiators. So what is the function of thermostats which are used in radiators? Control the velocity of water, control distribution of water to various cylinders, control the water temperature, control the pressure of water. Thermostat. The name itself suggests it is used to control the water temperature, which will prevent the water from getting extremely heated up and ensure that once the water reaches a particular temperature, it goes to the radiator and cools down. So the answer is C. As this is regarding compression ratio and the heat rejection. So as the compression ratio increases, there is a large increase in heat rejection, a large decrease in rejection, marginal increase in heat rejection, and marginal reduction in heat rejection. So what will be the answer as the compression ratio increases? Heat rejection to the cooling water cycle. So what we can say is that as the compression ratio increases, there will be for an SA engine there will be an increase in efficiency, uh, and the efficiency is directly proportional to the work power output. And for a constant heat input, work output increases slightly. It can't keep on going increase. It can't keep on increasing. There will be a peak point where the work output increases. But for a same heat input, work output increases and correspondingly rejected decreases. So there will be a slight decrease in the rejection of heat when the compression ratio increases. So the answer will be this one. So it can't keep on we can't keep on reducing the rejected forever. There will be a stalling effect after some while where it remains a constant. Yes. The fifth question is regarding air cooling in IC engines. Direct system of cooling air. Direct system of cooling air is one in which cooling water flows by gravity. Hot water is continuously cooled and circulated. Hot water is simply discharged. Water is allowed to evaporate in the cylinder jacket. So the direct system of cooling air is the one in which the hot water is not recirculated; it's just simply discharged. So this is one method of cooling. Where the hot water is completely discharged into the open air, and we do not reuse the hot water. We again we there will be a continuous supply of cooling water in this case. So the sixth problem is regarding the formula for the heat absorbed per kg of coolant air. In the evaporative cooling system, the heat absorbed per kg of coolant air is given by Cp delta T, Cv delta T, Cp minus Cv delta T, or latent heat of the coolant. The question is regarding evaporative cooling system, not a direct cooling system where the heat absorbed from the cylinder is used to sensibly change the temperature of the coolant. Here, it's a evaporation process which takes place where the coolant absorbs heat from the cylinder, evaporates and become vapor. So in this kind of cooling system, the heat absorbed per kg of the coolant is given by the latent heat of the coolant. So the heat absorbed per kg of the coolant per kg of coolant air is equal to latent heat of the coolant. So Q absorbed, actual Q absorbed per kg is equal to uh, the mass fraction, the latent heat of vaporization, delta H latent of the coolant. So this is regarding the kind of pump which is used in the forced cooling systems. So what will be the which will be the type of pump that is being used in force cooling system? Is it a piston pump, or a gear pump, or a vane pump, or a centrifugal pump? The pump which is used in the force cooling system is mainly centrifugal type of pump. Is the screen visible or
Yes, sir, is visible.
yeah. Am I audible?
Yes, sir.
So the main type of pumps which are used in the force cooling system are centrifugal type of pumps. The other type of pumps are not used. So this is regarding the advantages of liquid cooling systems. They are dependent only on water supply. Power absorbed by the pump is considerable, even cooling very cheap. What will be the possible advantages of liquid cooling systems? So there are two types of cooling systems. One is air cooled system and liquid. Second one is liquid cooling system. So the advantage of liquid cooling system. The advantage of liquid cooling system will be it provides an even cooling throughout the cylinder. It is not cheap. Uh, the power required to circulate water will not be that much, and it is not at all dependent only on water supply. It can take other liquids also. But and in order to cool the water, it requires additional air also. But the single important advantage it can offer is that it can provide even cooling. And what will be the limitations of air-cooled systems? Applicable only to large engines. Cooling is fast, uh, higher working temperature compared to water cooling, all of the above. What will be the limitations of air cooling systems? So the main disadvantage of air cooling system are that it has got a higher working temperature compared to water cooling systems. So the cooling compared to the water cooling system, uh, the cooling the cooling capacity achieved by air cooling system will be less, and because of that, the total cylinder will be at a higher temperature compared to that of a water cooling system, and chances of knocking are more in case of SA engines if we are using air cooling system. It is applicable to small engines, and the cooling is not that fast. So the limitations of air cooling systems are higher working temperature compared to water cooling system, and it doesn't offer an even cooling compared to water cooling system. what will be the main purpose of thermostat in an engine cooling system? Will it be to indicate to the driver the coolant temperature, pressurize the system, prevent the coolant from boiling, or allow engine to warm up quickly?
D, sir. D, I guess.
No, it's actually it will allow the engine to warm up quickly. That so actually it keeps on thermostat keeps a record of the temperature, right? So it will not allow the just like an air cooler system to get to a particular temperature and then go to somewhere else. It will allow the temperature to maintain a particular temperature and it reaches there quickly. So basically, the main purpose of a thermostat in an engine cooling system is to warm the engine quickly. To warm up the engine quickly. Okay. The next question is regarding the main purpose of uh, a fan in a liquid cooling system, whether it is to disperse engine fumes, whether it is to pump cold air over the hot water, or cool the external surface of the engine, or drive airflow when the vehicle speed is low.
B, sir. B, I guess.
Right, right. In the previous question, the main purpose of a thermostat in an engine cooling system, it will be allowing the engine to warm up quickly. So you got it right answer. And
Yes, sir.
once warm up temperature is being achieved, it will be trying to maintain that temperature for a while. Okay. Now we can move into some questions. Questions regarding the IC engines syllabus we have studied till now. This is regarding question. This is a question regarding the indicator power of the engine. So I'll just I'll give you 1 minute just to read through to go through it, and I'll try to explain how it is been done. Okay, let me go to this question. The following observations have been made from the test of a four-cylinder two-stroke gasoline engine. So keep in mind it's a four-cylinder engine and a two-stroke engine, not a four-stroke engine. It has got a diameter of 10 centimeter, stroke of 15 centimeter, a speed of 1600 rpm. Area of the positive loop of the indicated diagram is 5.75 square centimeter. Indicated diagram between pressure and volume, taking all the state points, all the endpoints into account, and we will be uh, actually the in the problem is being given the area of the positive loop. The it will be the loop will be clockwise in the case of a positive loop, and it will be negative in the case of a it will be anti-clockwise in the case of a negative loop. The area of the negative loop of the indicator diagram is 0.25 square centimeter square, and length of the indicator diagram is 55 millimeter. Spring constant is 3.5 bar per centimeter, and we have to calculate the indicated power of the engine. This is a question regarding the engine performance and characteristics. Uh, and this is one another by taking the area of the indicated diagram, we can calculate the indicated power. So that is another way of calculating the indicated power from the graph. Apart from the normal ways of calculating based of the brake thermal power as well as the frictional power, we can calculate the indicated power using this method as well. So has anyone tried to solve it? So has anyone tried to solve it, or has anyone got any answer?
No, sir.
Yeah, yeah, right. Right. So I'll try to solve. So in this particular problem, if you try to, so if I try to plot the PV diagram, so this is the intake, this is the compression, and if it is a SI engine, it will be constant volume heat addition process, and then there will be isentropic expansion, and there will be constant volume heat reduction, and then the final step of exhaust. So, this is the positive loop clockwise, this is clockwise, and this is the anti-clockwise loop that is negative. Because it's not that visible, I'll just try to draw it better. Better. So this is the positive loop and this is the negative loop. Positive loop is the upper part, which is the clockwise in the graph, and the negative loop is the anti-clockwise part. So in this given problem, the area of the positive loop is given as 5.75 square centimeter, and the area of the negative loop part, that is this part is given as 0.25 square centimeter. So total net area of the diagram equal to 5.5, 5.75, 5.75 minus 0.25. So it will be coming around 5.5 square centimeters. So we have calculated this. Then it's been mentioned the length of the indicated diagram is 55 millimeters. And if you have to calculate the average height of the diagram, we have calculated the net area of the diagram. And next we have to calculate the average height of the diagram. How to calculate the average height? Average height of the diagram. Average height of the diagram is given by the net area of the diagram divided by the length of the indicated diagram. So net area divided by length of the indicated diagram. Indicated diagram. So that is you'll get it around the net area of the indicated diagram is 5.5 centimeters square divided by length of the indicated diagram is 55 mm, that is 5.5 centimeters. So it is coming around 1 centimeters. So now the next step will be to calculate the indicated mean. So the actual value will be around 1 centimeter multiplied by the 3.5 bar per centimeter. So it should be 3.5 bar. That will be the indicated mean effective pressure. So in this question, we have to calculate the indicated power of the engine. Since we have got this indicated mean effective pressure, we can calculate the power using the formula. Power. Indicated power P is equal to PIM multiplied by the volume the volume of the stroke volume, that will be given as length into area into number of cylinders divided by 60,000. So in the case of this is a two-stroke engine. So two-stroke engine, that's why this K is the number of cylinders and will be the bore cross-sectional area pi by 4 into d bore the whole squared, bore the whole square, multiplied by the RPM n. Number of cylinders will be 4 multiplied by RPM. This is the RPM multiplied by 1 by 2 or 1 depending upon it is a two-stroke or a four-stroke cylinder. This is the number of cycles per second. So the number of cycles per second uh, for a four-stroke engine, it will be so this is 3.5 bar multiplied by 0.15 into 5 by 4 into the bore diameter of the bore is 10 centimeter, so it's 0.1 squared into number of cylinders is 4, number of cycles or number of E is equal to number of RPM is equal to 1600, 1600, 1600 divided by uh, it, you have to calculate it in terms of kilowatt. So that's why we have divided by 1000. So this will be equal to 3000. So it will be coming around 3.5 bar. If you write it properly, it will be into 10 power 5. It will be coming around 43.98 kilowatt. So the indicated power of the engine can be calculated from the uh, indicator diagram using the area of the indicator diagram. Net area is equal to the area of the positive loop minus area of the negative loop. That divided by the length of the indicator diagram will be giving the average height of the diagram. Multiplying the average height with the spring constant, we'll get the indicated pressure. And using the indicator pressure, we can calculate the indicated power by multiplying the stroke volume, the number of cylinders, and also taking into account the number of cycles per second. For a four-stroke engine, it will be equal to number of RPM. For a four-stroke engine, it will be number of RPM divided by 2. For a two-stroke cylinder, it will be number of RPM. Number of cycles will be equal to number of RPM. So the indicated power is 43.98 kilowatt. So the next question is regarding powers, different powers. We have to calculate the friction power loss as a percentage of the brake power. A single cylinder engine running at 1800 RPM develops a torque of 8 Newton meter. So the indicated power of the engine is 1.8 kilowatt. We have to calculate the loss due to friction power as the percentage of brake power. So in this particular problem, this is a simple question. We can calculate it by using the standard formulas available. We can calculate the brake power from the torque of the engine. Uh, And using the brake power, we can calculate the friction power as the indicator power is given in this program, and then we can calculate the percentage of the brake power, friction power as a percentage of the brake power. So the friction, the brake power is given by the formula uh, 2 pi n into torque divided by brake power in terms of kilowatt, 60,000 equal to 2 pi into it's a single cylinder engine and running at 1800 rpm. So nothing is given regarding the whether four stroke or two stroke. So we can directly calculate the 1000 rpm to be equal to number of cycles. 2 pi into 1800 into torque is 8 Newton divided by 60,000. So it will be coming around 1.508 kilowatt. Then we have to calculate the indicated, we have to calculate the friction power. Friction power is equal to kilowatt is equal to indicated power minus of brake power, that will be equal to 1.8 minus 1.508 will be equal to 0.292 kilowatt. So the percentage loss equal to friction power divided by brake power multiplied by 100, that will be equal to 0.292 divided by 1.508 multiplied by 100, it will be coming around 90.36 percentage. The next question is regarding indicated thermal efficiency of the engine. Uh, it's an Otto cycle, consumes 8 liters of gasoline per hour and develops 25 kilowatt. The specific gravity of the gasoline is 0.75 and its calorific value is 44,000 kilojoules per kilogram. We had to calculate the indicated thermal efficiency of the engine. Indicated thermal So heat equivalent of the indicated power divided by the heat input will be giving the indicated thermal efficiency. So in this particular problem, it's been mentioned indicated thermal efficiency ITH equal to heat equivalent of indicated power divided by heat input. So it will be equal to 25 kilowatt it develops a 25 kilowatt indicator power, so it's multiplied by the amount of specific gravity of the fuel is 0.75 and 8 liters is equal to 8 into 10 power minus 3 multiplied by 750 multiplied by 4,400 kilojoule per kilogram. This 25 kilowatt uh, multiplied by this we have to this is in terms of 8 liters per hour. So we have to uh, multiply it by the mm, we have to we have to calculate the value in terms of per second. So it will be multiplied by 60 into 60. So we'll be getting it around uh, 34.1 percentage. Okay, the next question is regarding the indicated thermal efficiency. If the calorific value is given, and it's a similar kind of a question to that of the previous question. We have to calculate the indicated thermal efficiency if the calorific value of the fuel is 43 megajoules per kilogram and the engine uses 360 grams of gasoline per kilowatt hour. Uh, so in this particular problem, uh, we are being given a four-cylinder engine running at 1200 RPM and it delivers 20 kilowatt of power. The average torque when one cylinder was cut is 1100 Newton meter. Uh, it was initially a four-cylinder engine, now it has become three-cylinder, and the average torque for three-cylinder engine is 110 Newton meter. We have to calculate the indicated thermal efficiency if the calorific value of the fuel is 43 megajoules per kilogram and the engine uses 360 grams of gasoline per kilowatt hour. How will you approach this kind of a problem? So the average brake power for three cylinders will be given by 2 pi n t divided by in terms of kilowatt 60,000. So n will be it's a four cylinder engine and n will be given as 1200 rpm and nothing is mentioned whether this is a four stroke or a two stroke engine. So we can directly take the number of cylinders, number of rpm is equal to number of cycles is equal to number of rpm. So 2 pi into 1200 multiplied by 2 pi into 1200 multiplied by torque is given as 100 ton divided by 60,000. So it's coming around 13.82 kilowatt. And next, we have to calculate the So the average brake power for three cylinders, we have calculated as 13.82 kilowatt. Now we have to calculate the average input, average indicated power for one cylinder. So the average indicated power, uh, average indicated power with one cylinder is equal to 20 minus 13.82 equal to 6.18 kilowatt. So the total indicated power IP is equal to 6.18 into 4, that is equal to 24.72 kilowatt. Now we have calculated the total indicated power. We need to calculate in this particular problem indicated specific fuel consumption, specific fuel consumption ISFC, that's equal to the brake specific fuel consumption which you have given in this problem, BSFC multiplied by the brake power divided by indicated power. So the value of indicated specific fuel consumption multiplied by the indicated power will be equal to the brake specific fuel consumption multiplied by the brake power. So as the total fuel consumed is independent of whichever method we adopt for denoting it for it is independent of the nomenclature procedure. So BSFC is uh, this particular problem. It's been given as 360 grams of gasoline per kilowatt hour. Brake power will be given as 20 for four cylinders. 20 for four cylinders and and uh, and divided by the indicated power. Indicated power will be around 24.72. So the value will be coming around 291.26. It will be lesser than the brake specific fuel consumption as indicated power is more. Gram per kilowatt hour. Finally, we need to calculate the fuel consumed. We have calculated the indicated specific fuel consumption. The next step is to calculate uh, the fuel consumption based on the actual value. It will be this is in terms of gram per kilowatt hour. We need to calculate the fuel consumption uh, in terms of kilogram per second, and based on that we can calculate the indicated thermal efficiency. So the next step will be to calculate the uh, fuel consumed in terms of kilogram per second to the indicated specific fuel consumption multiplied by indicated power, indicated power divided by this is in terms of uh, 24.72 is in terms of kilowatt, and this is in terms of kilogram per kilowatt hour, in gram per kilowatt hour. So we divide the whole thing by 1000 to get the value in terms of kilogram per second, and kilowatt hour we need to the hour we need to calculate in terms of seconds. So we convert by using 3000. So so the value will be coming around 291.26 multiplied by indicator power is 24.72 divided by 3600 into 1000. It will be coming around 2 into 10 power minus 3 kilogram per second. And we can calculate the required uh, quantity in this question, that is indicated thermal efficiency. So theta ITH is equal to the indicated power divided by mass flow rate of the fuel, that is this particular value, into calorific value. So it will be coming around 24.72 divided by 2 into 10 power minus 3, 2 into 10 power minus 3. Mass flow rate is given as 2 into 10, we found it out as 2 into 10 power minus 3, and calorific value is given this problem 43 megajoule per kilogram. So it should be 43 into 10 power 43,000, 43 into 10 cube. Will be coming around 28.74 percentage. Right. The bore and stroke of a water-cooled vertical single-cylinder four-stroke diesel engine are 80 millimeter and 110 millimeter respectively. So we need to calculate the torque is given as 23.5 Newton meter. We have to calculate the brake mean effective pressure of the engine. So in this particular problem, the power is given as brake power is given as 2 pi nt divided by 60,000 in terms of kilowatt. So it will be 2 pi. So the same quantity 2 pi into n we did not know. We do not know. And torque is 23.5 divided by 60,000. This is first formula. The second formula for brake, this is from the torque. The same quantity of the brake power can be expressed in terms of the brake mean effective pressure. So power kilowatt is equal to uh, brake brake mean effective pressure into the volume of the stroke, length of the stroke that is equal to the length of the stroke multiplied by the area of stroke multiplied by the number of cycles uh, divided by 60,000 terms of kilowatt. So the n is equal to this quantity we do not know. Uh, we have to calculate the values based on we have to calculate this brake mean effective pressure. So by equating these two, we can get the value. And how will you get it? So the brake mean effective pressure. Uh, these two will be equating. This and this will be equating to get the value of brake mean effective pressure is equal to 2 pi nt 2 pi into n into torque divided by length into area into number of strokes. So 2 pi into is equal to RPM. RPM is RPM. This is cycles per minute. Length into area into n by 2 for a four-stroke engine. And in this particular problem, number of cylinders is equal to 1, so we need not take into account of that. So the these two get cancelled out, so it will come around 4 pi into torque is 23.5 divided by uh, pi by 4 into area bore diameter is uh, 80 millimeters, so it's 0.08 squared multiplied by 11.11 multiplied by 0.11 multiplied by yeah, that's it. And we have already taken into account the number of RPM and number of cycles per second in this program. Uh, so, so it will be coming around 16 pi into 23.5 pi into 0.08 into 0.11. So it will be coming around this pi and pi gets cancelled out. So it will be coming around it will be coming around 5.3 bar. 3, 4 bar. So the indicated the brake mean effective pressure is equal to 5.34 bar. So in this particular problem, we have to calculate. We have to calculate the brake specific fuel consumption in terms of kilogram per kilowatt hour of a diesel engine whose fuel consumption is 5 grams per second when the power output is 80 kilowatt. If the mechanical efficiency is 75%, calculate the indicated specific fuel consumption. I'll give you 1 minute to look in this problem. This is just a continuation of the problem which we have seen in the previous questions. To calculate the brake specific fuel consumption for a diesel engine, fuel consumption value is given as 5 gram per second. The power output is given as 80 kilowatt. Mechanical efficiency is 75%. We have to calculate the indicated specific fuel consumption. So the in this particular problem, the brake specific fuel consumption uh, is equal to mass flow rate of the fuel divided by the brake power. It's given by 5 gram per second. Brake power is 80 kilowatt equal to 5 by 80. It will be coming around 0.0625. 0.0625 it's gram per kilowatt second. So the brake specific fuel consumption will get, and we'll just convert that into the standard format. Uh, and second to our, we have to divide, by 3,600 gram to kilogram. We have to divide by 1,000. So the whole quantity we multiplied by 3.6 to get the value in kilogram per kilowatt hour. So it will be coming around 0.225 kilogram per kilowatt hour like specific fuel consumption. So the indicated specific fuel consumption is equal to brake specific fuel consumption multiplied by the mechanical efficiency that will be equal to uh, the mechanical efficiency is equal to the indicated specific fuel consumption divided by brake specific fuel consumption. The mechanical efficiency formula is brake power divided by indicated power. So this brake power can be written as brake power divided by mass flow rate of fuel. This is also equal to indicated power divided by mass flow rate of fuel. So it will be equal to 1 by brake specific fuel consumption divided by 1 by indicated specific fuel consumption, that is equal to ISFC divided by PSFC. So the indicated specific consumption is equal to brake specific fuel consumption multiplied by the mechanical efficiency. So we'll get it as 0.225 multiplied by 0.75. That will be around 0.169 kilogram per kilowatt hour. So this question, in this particular problem, we need to calculate the air fuel ratio of a four-stroke single cylinder air cooled engine with a fuel consumption time for 10 cubic centimeter, 10 centimeter cube to be 20.4 seconds, and air consumption time for zero point 0.1 meter cube is 16.3 seconds. The load is 70 kilogram at the speed of 3000 rpm. We have to also calculate the brake specific fuel consumption in gram per kilowatt hour brake thermal efficiency. In the density of air of 1.175 kilogram per meter cube, and the specific gravity of the fuel to be zero point 0.7, and the lower heating value is 43 megajoule per kilogram, and the dynamometer constant, which will be used to calculate the the, the dynamometer constant in this particular problem is given as 5000, and that will be used to calculate the power output. I'll give you a minute to just reading the problem and try to solve it. In this particular problem, I'll try to solve it. The air consumption value. Air consumption value will be given as uh, 0.1 meter cube divided by 16.3 second multiplied by the density 1.175 So it will be coming around 7.21 into 10 power minus 3 kilogram per second. The next quantity we have to find is fuel consumption in terms of kilogram per second, same unit. So in this particular problem, we have been given 10 centimeter cube. So 10 into 10 power minus 6 multiplied by the density is 700 and the time taken for this much flow is 20.4. So that will be coming around 0.343 into 10 power minus 3, 0.343 into 10 power minus 3 kilogram per second. So we need to calculate the air fuel ratio, the first objective of this particular problem. So the air fuel ratio equal to mass flow rate of air to the mass flow rate of fuel. That will be equal to 7.21 into 10 power minus 3 multiplied by 0.343 into 10 power minus 3 equal to 20. So since this can be considered to be that of a lean, it's an air-cooled engine with fuel consumption time per cost of a single cylinder. So it can be considered to be lean operating conditions. And the power output P can be given by the formula. The In this particular problem, we need to the dynamometer constant is given as 5,000 and the load is 17. Beg your pardon. This is actually 7 kilogram at the speed of 3,000 RPM. So there is a mistake. So the load is 7 kilogram at the speed of 3,000 RPM. So and the dynamometer constant is 5,000. From these three quantities, we can calculate the power output from the engine. So the load is 7 kilogram, and the RPM is 3,000, and the dynamometer constant the value is 5,000. So the value will be coming around 4.2 kilowatt. The dynamometer constant unit will be in terms of kilogram into RPM, number of revolutions per second, multiplied by number of revolutions per minute, multiplied divided by the kilowatt. So this should be the unit of dynamometer constant. So that's given in this particular problem to be 5,000. So the value of the power output is equal to 4.2 kilowatt, and we need to calculate the brake specific fuel consumption as well as the brake thermal efficiency. So in order to calculate the brake specific fuel consumption, In terms of gram per kilowatt hour, we have got the fuel consumed, fuel consumption in terms of gram per hour, and the power output in terms of kilowatt. So it should be coming around the fuel consumption value. Mm. Fuel consumption value will be coming around from the previous analysis. We have calculated with 0.343 kilogram per second. So it will be around 0.343 into 10 power minus 3. This value was in terms of kilogram per second. We multiply it by 1000 to get gram, and in order to get in terms of second, we divide by 3600. Sorry, this value was in second, so we multiply it by 3600. I beg your pardon. And the power output in terms of kilowatt is 4.2. So the answer will be coming around that's 294 gram per kilowatt hour. 24 gram per kilowatt hour. This is gram. Gram per kilowatt hour. And finally, we have to calculate that calculate the brake thermal efficiency (BTH). So it should be eta brake thermal efficiency is equal to the brake power divided by the input calorific value multiplied by the mass flow rate of fuel. So mass flow rate of fuel will be 0.343 into 10 power minus 3 kilogram per second multiplied by the calorific value will be equal to 43 megajoules, 43,000. So brake power in terms of kilowatt we have to provide it. So it should be 4.2 divided by so the efficiency is coming around brake thermal efficiency is coming around 20.48%. So a gasoline engine has a stroke volume of 0.0015 meter cube and a compression ratio of 6. At the end of the compression stroke, the pressure is 8 bar and the temperature 350 degrees Celsius. Ignition is set so that the pressure rises along a straight line during combustion and attains its highest value of 25 bar after the pressure has traveled 1 by 30 of the stroke The charge consists of a gasoline-air mixture uh, in proportion by mass 1 to 16. Take R value, gas constant of gas constant value equal to 287 joule per kilogram Kelvin, and calorific value of the fuel 42 megajoule per kilogram. Cp equal to specific heat of air to be equal to 1 kilojoule per kilogram Kelvin. Calculate the heat lost per uh, kg of charge during combustion. We have to calculate the heat loss per kg of charge during combustion, and we know the R value of air, Cp value of air, and calorific value of the fuel. The equation is said so that the pressure rises along a straight line during combustion and attains a high value of um, attains its high value of 25 bar after the piston has traveled 1 by 30 of the stroke. So the highest value of the pressure is attained after the piston has traveled 1 by 30 of the stroke. So after the TDC, it travels 1 by 30 of the total stroke length towards the BDC, bottom dead center, to attain its highest pressure. It's been mentioned that the pressure at the end of the combustion stroke is 8 bar and a temperature of 35. So the highest pressure will be occurring after the highest TDC, the TDC. It will be during the power stroke, and the highest pressure will be at 1 by 30 the distance of the total time. So we have to calculate the heat loss per kg of charge during combustion. So I'll give you a couple of minutes to just read through this problem, and meanwhile I'll also try to solve it. So in this particular problem, the gasoline engine has a stroke volume of 0.0015 meter cube. So that's the first step. The second one, we have to calculate. Uh, we have to just note the input values in this particular problem. So stroke volume is given as 0.0015. And if we try to plot these points in a PV diagram, hopefully. So if you ignore the suction, start from the beginning of compression, one, two, let's say gasoline engine, SI engine. So the heat addition will be constant volume. So straight process. But in this particular problem, it need not be. As the maximum pressure will be attained. The maximum pressure will be attained after it traveled 1/30th of the stroke. So in this particular problem, there is a slight difference. Uh, though it is a SI engine, and the peak pressure doesn't occur at the clearance volume. Uh, the it happens. It have in this particular problem. It happens at 1/30th of the stroke away from the clearance volume. So let me draw it a bit more clearly. Right. So the actual cases will be like this, but in this particular problem, it happens slightly away. So this will be the actual three, and this is the Otto cycle maximum peak pressure. Then it undergoes isentropic expansion and then heat rejection constant volume process. So if you try to project it onto the volume axis, so this is the clearance, this is the clearance volume, this is the total stroke volume, and this will be the 1/30th of the stroke volume. In this particular problem, uh, in terms of uh, meter cube, if you write Vs is equal to 0.0015, and this particular V dash is equal to 1/30th of 0.0015. So that will be around this V dash will be equal to, so it will be around 5 into 10⁻⁻5 meter cube, and VC control clearance volume is equal to, we have to calculate from the compression ratio. So VCV, the equation of the compression ratio is equal to V control volume plus V stroke volume divided by, sorry, V clearance volume plus V stroke volume divided by V clearance volume. 1 plus V stroke volume divided by V clearance volume. We know the value of V stroke volume equal to this 0.0015, and clearance volume is equal to, sorry, compression ratio is equal to, compression is equal to 6. So in this particular problem, compression ratio value is equal to 6. So the value of clearance volume uh, we get as the stroke volume divided by the stroke volume divided by 5. That will be around 0.0003 meter cube. So we know the value of V control volume, V stroke volume, and V dash. So the actual then we can calculate the value of the volume at the point 3. In this particular problem, V3 V clearance volume plus V dash that will be around 350 point 0003 plus equal to point 00035. So so it will be around 0.00035 meter cube, and we need to calculate the temperature at the point 3. We know the temperature at the point 2. This should be 2. The temperature at the point 2 will be equal to in this particular problem. It's been given us the pressure is 8 bar and 350 degrees Celsius at the end of compression. So it will be 350 plus 273. It will be around 623 Kelvin, and T3 will be around. You can calculate from the PV equal to nRT for ideal gas equation. PV by nRT is a constant, so PV nR remains a constant in all the cases. So PV by T of the second case is equal to PV by T of the third point. So from this T3 is equal to PV of 3 into T2 divided by PV of 2. Uh, so T2 is equal to 623 multiplied by PV3. PV pressure at the end of the compression. It's a peak pressure that's equal to 250. It's given the problem was 25 bar. So you can write it as 25, and pressure before compression is equal to 8 bar, and the volume at the end of the compression V3 is equal to 350 point 00 0.35 divided by volume at the beginning of the compression, that is a clearance volume. Clearance volume is equal to 0.0003, 0.0003, 0.00, beg your pardon, there is one more zero is there. So 0.0003, okay, right. So the value of T3 will be equal to the temperature at the after the compression. After the compression, the temperature at the peak value of the temperature and pressure during the combustion process. So that is T3. So T3 will be equal to 2271 Kelvin. So then we have to calculate the heat uh, the heat actually given in the mixture in one cycle. So in this particular problem, we need to calculate. mm, we have to calculate the heat loss per kg of charge during combustion. For that, we need to calculate first of all the quantity of heat actually given to the mixture in the cycle, and to calculate that, we need to calculate the work, the quantity of the quantity of work done. Uh, so in order to calculate the heat added to the mixture during the process 2 to 3, we need to calculate since this is not a constant volume process, we need to calculate the work done and the change in internal energy, change in internal energy from 2 to 3. So we have to calculate the work done in this process. So work done from 2 to 3 will be equal to the we calculate an average pressure since pressure is not a constant. 25 after the combustion and 8 before it. We take an average pressure T mean of the process multiplied by the change in uh, volume. So it will be around 0.0005, 0.0005. So so it will be coming around. It will be coming around. So it will be coming around to 82.5 joules. Kilojoule. And now we have calculated both work done in this process as well as the change in internal energy and therefore we can calculate the heat added to the mixture in the process Q23 that is equal to delta E23 plus W23, that will be the final value will be 1.572 plus 82.5 82.5 joules. So that will be 0.0825 joules. So it will be coming around uh, 1 point, just 1.6, around 6. One point six 1.657. It will be coming around 1.65, close to 1.657 kilowatt. No, it should be kilojoules. Beg your pardon, it should be kilojoules. And we have calculated the heat, quantity of quantity of heat added in the process, heat added in this process. Uh, we have calculated this one. The next step is to calculate uh, the heat loss during explosion. Uh, in this particular problem, uh, that will be equal to so the charge consists of a gas and air mixed by proportion by. Yes, the next step we have to calculate the quantity of heat lost per kg during the combustion. Uh, this is the value which we have calculated based on the diagram as well as the actual pressure and temperature. But from the calorific value of the fuel, we would actually get the input value of heat that would have been given to the system had there been uh, no losses. So, so the actual input heat from fuel is given by mass flow rate of the fuel multiplied by calorific value of the fuel. So in this particular problem, so we know the mass flow rate of the mixture mass to be 1.342, and the fuel the air to fuel ratio the air to fuel ratio will be equal to 16:1. So the actual proportion of the fuel in the air fuel mixture will be equal to 1 by 70. So the mass flow rate of fuel will be equal to mixture mass divided by mixture mass mixture mass divided by uh, 70. So it will be 17. This is equal to 1 plus air fuel ratio. In this particular problem, it's 16. So it's coming around 1.342 into 10 power minus sorry 10 power minus 3 10 power minus 3 divided by 17 multiplied by the calorific value of the fuel should have been 142,000 kilojoules per kilogram. So we can calculate the actual input ratio input the heat from the fuel to be equal to 3.3 3.31 close to 3.31 55 kilojoules. So we have calculated the actual input the heat from fuel and the heat lost in this process during the heat addition from 2 to 3 in kilojoule per kilogram will be equal to 3.3155 minus 1.657. Sorry. So the value will be around 1.65, close to 1.65 kilojoule per kilogram. I'm sorry, he lost it in kg terms, so it should be kg, kj. In this particular problem, but we have to calculate the heat lost per kg. So the heat lost in kilojoule per kg terms is equal to 1.65. 1.65 divided by 1.342 into 10 power minus 3. That will be equal to 1234 kilojoule per kilogram of, of mixture. So heat loss in kilojoule per kilogram will be 1.1234. So totally we'll calculate. So in this particular problem, we have to calculate the heat loss per kg of charge during combustion. For that, first of all, we need to calculate how much is the total input of heat during this process. This is not a constant volume or nor a constant heat addition process. This is in-between process since it's been mentioned that the highest peak pressure, the peak pressure obtained at a stroke 1/30 of the stroke length. So we need to calculate the actual heat added in this process. For that, we need to use the uh, ideal gas equations. We have to calculate the work done in this process, and we have to calculate the internal energy change in this process. The addition of this work done and the internal energy process between 2 to 3 will be giving the heat added in this process. Then we have to calculate the actual input of heat based on the calorific value of the fuel. Separating that, we'll be getting the heat loss per kg during the combustion. So the value of the heat lost during this process is 1,234 kilojoule per kilogram of mixture. Okay. The next is a question based on the octane number of the SA engine fuel. So this is an MCQ. If the octane number of SA fuel is higher, the fuel has got higher heating value, longer ignition delay, lower volatility. What will be the answer? Uh, the important thing to notice that this is an SI engine fuel and the octane number. Higher the octane number, the lower the chances of knocking. So what should be so this is completely opposite to the quantity which uh, we refer to in the case of a CA engine. CA engine is called a CT number, where the fuel should be having comparatively less ignition delay. It should start the auto ignition quickly. But here, the fuel should be having sufficiently high uh, auto ignition. to prevent it should be having sufficiently high auto ignition temperature to prevent the self ignition. So the if the octane number of the SA engine is fuel, that means that it's a better fuel to prevent the knocking in the case of SA engine. It prevents auto ignition. That means that it will be delaying it will be the ignition delay will be getting longer, and the flame will be having sufficient time to meet the end charges before it starts to auto ignite. So the answer is longer ignition delay. What are the two important modes of heat transfer in cooling systems of IC engines? So the cooling happens mainly by using conduction and convection. From the outer part of the cylinder, conduction happens to the conduction happens to the water jacket, and the convection happens to the air outside. So the conduction and convection are the two modes of heat transfer in cooling system in IC engines. So in IC engines, so the next is a question regarding the uh, engine size, speed, and load effect on the engine cooling characteristics. So in IC engines, dash speed, dash load, and dash engine size offers higher enhancement in the engine cooling characteristics. Uh, this is based on the lecture. Um, higher the speed, higher the load, and higher the engine size enhances the engine cooling characteristics. Higher the speed introduces better uh, turbulence and higher heat transfer coefficient. Because of that, heat transfer between the mixture as well as the surrounding cylinder increases. Second one, higher the load means more means throttle will be open to its fullest, and more air fuel mixture will be entering. More fuel air fuel mixture, more Reynolds number will be high, and Reynolds number will be high means uh, higher heat transfer coefficient and better complete total heat transfer between the mixture and the cylinder. And the third is the engine size. As the area increases, total heat transfer coefficient increases. Total heat transfer increases. So in case of speed, uh, better turbulence, higher H value. So H is equal to heat transfer is equal to HA into delta T. So either H or A can be increased to increase the delta Q. So speed, higher the speed, better turbulence and better heat transfer. Better heat transfer increases, heat transfer increases, and then the load increases, more air plus fuel, higher Reynolds number, higher heat transfer coefficient, some rule, and better heat transfer. So, and the third one, engine size increases, area increases, and then heat transfer, total heat transfer. It can be either to increase in heat transfer, or it can be through increase in area. So heat transfer increases. Okay. This actually concludes this movie. Yes. Uh, these are the basic questions which we have discussed in this lecture, the previous 2 hours, and we mainly discussed about a few multiple choice questions regarding the heat transfer and energy distribution, and a few problem on octane number, cooling system, and a lot of problems on numerical type problems on IC engines regarding the various type of break efficiencies, break thermal effective, uh, break thermal efficiency, indicator thermal efficiency, as well as different mean effective pressures. And I hope you have understood what we have discussed in this lecture. Uh, and we will meet in the next class based on the lectures of the next week. And most probably it will be on gas turbines. Thank you.